So let's get started. I'm Kan, and Kai's the other presenter. Thank you guys for coming today. I know there's a lot of different time zones, so thanks for accommodating our schedule. But this is the presentation on an introduction to CAD and mechanical design. Yep. So as an agenda,
So
Kai.
the agenda, we're gonna introduce ourselves. We're gonna give an overview about mechanical design, CAD, and the engineering process in general. And then we'll go talk about the applications of CAD, especially in robotics and research projects. We will briefly introduce some resources and then finally hold a Q&A session.
So you guys can drop the questions in the link I sent in the Discord before, or you could just ask them in chat or something at the end. So, introductions. I'm Khan. I'm a rising junior at Peninsula High. I'm the engineering director at First Robotics Team, Team 2637, which is the local high school's robotics team. I was previously on the mechanical design team. At IgniteMinds, I'm the blog editor and writer. I'm a research mentor, hence the presentation, and I'm also leading Team 2 of the research teams, where we're focusing on ventilator design. I'm also a team captain of a TSA team. We placed second place in California last year, and we placed third nationally in digital media in 2019.
Okay, I'm Kai Shimada. I'm Khan's twin and basically right-hand man. Pretty much everything is the same. Yeah, next slide.
All right. So we're gonna begin overviews of a lot of the basic and high-level concepts.
So mechanical design, uh, it's the engineering of mechanical engineering. It's a branch of mechanical engineering and deals with the design of mechanical components. So we have to collaborate with electrical design, controls design, etc., to design entire systems. And these systems can range anywhere from small personal projects to full-on robots. Um, so the design process is the step before fabrication assembly, and they can be from sketches on a whiteboard and brainstorming to full-on CAD models. We try to iterate during the CAD process before they are actually manufactured and learn and gather data from prototypes so that we don't have to manufacture full-on robots before the final step because that would cost a lot of money. And each mechanical designer needs to see our design through until the end.
Okay, so you as the engineer, you as the mechanical designer, you are responsible for fulfilling the team objectives and requirements that are going to be given to you or that you're going to help develop. You're responsible for staying within design constraints, and we'll go over what they are later. Um, you're responsible, obviously, for creating a manufacturable, serviceable design that's possible to manufacture according to the machines and the resources that you have. You're responsible for integrating non-mechanical features. These would be pneumatic, electrical, other software requirements, and make sure that they can function properly within your mechanical design. You're also responsible for overseeing the completion and testing of your system, of your subsystem, possibly. You're also usually responsible for presenting those results and creating the next iteration of the design. If you aren't going to be making the next iteration, you can obviously delegate it to someone, but you're responsible for passing that knowledge on.
So
Okay, yeah.
what we design for. So when you are designing, when you are CADing or just brainstorming, you have to design with the stakeholders in mind. So a lot of the times it's the manufacturing fabrication, which is the capabilities that you have at hand. So if you have industrial grade machines, they even have limits, and you have to design your system so that they can be manufacturable. Another constraint can be time. You might be limited in time, and you might not be able to make your design as complicated or as fancy as you want, but you have to keep those in mind. And the end goal is your performance, system requirements, and your design constraints. So performance goals, you usually lay out before you start CADing, and these are what you want to achieve through what you designed. And the system requirements and design constraints are the constraints that prevent you from making super fancy and overcomplicated systems. They can be cost, time, or ability. These abilities can be manufacturing ability, or they can be programming ability.
Yeah, so another design constraint that you will most likely run into is cost, right? You're not gonna have an unlimited budget, and so you're gonna have to be able to say, hey, you know, you can't spend more than a certain amount on your mechanism, and also time, right? You don't have all of eternity. You're gonna have to, have goals and a schedule that you keep to.
So what is CAD? We keep throwing that term around. It's computer-aided design, and it's 3D modeling using computers and CAD software. So they have many advantages over just straight up building, prototyping. They are easy to edit, and they can make calculations for you fast, automatically, and accurately. They can help you visualize the entire system before you actually build it, which is super helpful, especially when you don't have time or that resources. And they let you test out mechanisms and look for mistakes before they are manufactured. For example, you can make sure that certain parts aren't hitting each other when they are moving, and you can prevent those in the CAD process. Next slide. So how do you CAD? So if you never touched CAD software, you can download one of many CAD softwares available online. Personally, I and most of the people around me use Artist Inventor, and that and it is taught at Ridgecrest. We just used it because we are used to it. Although switching between CAD systems can be easy or hard depending on which ones you are using. Learning how to use the CAD software is easy if you have good training materials, and mastering it can take many months. There's plenty of resources online. So in this presentation, we won't be teaching you exactly how to CAD, but we can guide you to online resources, and you can simply Google them to find many people who are willing to teach you CAD.
All right. So another aspect of design and CAD packages in general is FEA simulations. So FEA simulation stands for finite element analysis simulations. And this is a feature that's included within Autodesk Inventor. I know it's included within SolidWorks, which is another really popular CAD package. And there's many types of finite element analyses, such as stress analysis, dynamic simulation, and frame analysis. This basically finds out and tells you when you place a load on a certain part of your system, or maybe even a part. It tells you, this is where a lot of the stress is being placed. If you look at the example picture here, I don't know if you can see my mouse, but the blue parts, that means there isn't a lot of stress when the load is applied directly above this system. That means, the red parts have a lot of stress applied to them, and you'll be able to find the optimal solution. You can make sure that you're not using too much material, because you can have a hunk of aluminum, it'll be very strong, but it also wastes a lot of material and be very heavy and very expensive. Well, actually, it wouldn't be as expensive because you wouldn't be machining anything, but it'd be really ugly and heavy. Um, and you can also make sure that your parts aren't gonna break, and you can make sure it doesn't break before you make it. Other examples, you can make, if you have a bearing, for example, you can make a parabolic load where there's an axial or radial load. That's if you have like a bearing on like a drivetrain, for example. You can make sure that that bearing can withstand the load. You can make moment loads, where you specify along which axis the load is placed. That could be useful if you were, for example, designing a system that was supposed to support a lot of weight, and it's also supposed to roll on like a bar. All right, engineering drawings. So this is the quote unquote paper side of the mechanical design process, I'd say. There's two general types of engineering drawings. These are part and assembly drawings, and these drawings are things that you're going to be showing and sending and releasing to people who are going to be manufacturing the parts. Sometimes that's going to be you, but often in a more professional setting, that's going to be someone else, a subcontractor or a different sub team. And so part drawings, these are the individual parts in the assembly, right? These help manufacturers make the part, and it shows the critical dimensions on what's needed so that the part will function as intended. And it should also follow geometric dimensioning and tolerancing guidelines, GD&T. We're not going to exactly, go through what all of these are, but these are basically guidelines that engineers use to make sure that the drawings and the dimensions that they put in are accurate and they are necessary. Assembly drawings are basically like a massive advanced Lego kit, right? It shows how to assemble parts in the subsystem, and it also has a list of all the parts in assembly. Sometimes these can be substituted by a CAD model, where you give the CAD model to the people assembling the product, and they can go at it that way, or you can print it on big sheets of paper like here, and go about it that way. This one you can see, this is mostly linear in two axes. This was a very complicated mechanism. This was made in my freshman year, and you can also see that we have a list of materials so that these balloons specify, which part is what.
And also, that is a very bad example of a drawing. It looks overcomplicated and fancy, but you do not want to send those to whoever's assembling them, because they will get mad.
Yeah, they were not very happy about it, but that's yeah. So just make sure you're thinking about that as you design. So I've been throwing around the word engineering design process a lot. The full process, which includes the strategy, which is like what objectives you want, what requirements you have, and all the prototyping. I've detailed it in a blog, on an IgniteMinds blog, so I'll also link that later, and you can read through that. But for you as a mechanical designer, this is the part that you're concerned with, right? So you're going to be given, or you're going to have developed requirements and objectives. This is going to be, what do you want your thing to do? For example, if you're building a robot, what do you want your robot to do? Very high level. And then you're going to start off with ideas. We call them quote unquote whiteboard sketches, but these are just very, very rough sketches. It's literally just an idea, right? And a lot of ideas are going to be thrown around, and a lot of them are going to be bad, and a lot of them are never going to ever be made. But that's okay, because once you select a few that you want to pursue, you're going to look at prototyping them, and you're going to look at getting the necessary and critical geometry required for that part to function. If you were going to make an intake, for example, you'd have to see, what parameters and what dimensions do I need that are critical to the functioning of the intake, so that when you go into the CAD design phase, you know that these dimensions can't be contested, right? Those have to be what they are. And then you'd go through the CAD design process. This could take, weeks. If you're on a time constraint, obviously you want to hurry up. But eventually, you're going to have a design review or multiple design reviews, and you're going to get the approval, hopefully, for your mechanism. And once you have that, you're going to manufacture it, you're going to test it, you're going to apply the wiring, electrical wiring, you're going to apply the controls logic, and you're going to eventually iterate on that mechanism. Now, whether you iterate within the design phase, while it's still within the realm of CAD, or you're going to make a revision after it's all been tested, or somewhere in between. Maybe you find something that's wrong while you were assembling it. That's still an iteration, but it depends on your specific situation. Here we have a few examples of things we have during the design process. So on the left, you can see this sketch, right? What is this sketch? So this is a kinematic analysis. It's a review of the required geometry to accomplish the necessary functions. So on this one, you can see that it was supposed to be a mechanism to lift this cube to a certain height, to certain heights. And the people designing this saw that, maybe you wanted a linkage like this, right? And they would make this, this was done in CAD. You can make a 2D sketch like this in CAD, and it's very easy to move it around and change the necessary dimensions. But basically, they saw, before they even went into prototyping, they saw what needed to be done, and you can move the linkages around, you can move the joints around, and you can see what was most optimal. This is particularly good for things that require height, because you're going to be able to see where the specific linkages and joints have to be. On the right, you can see a complete CAD design. You can see that we have the electronics. These are the electrical components. You have the motors. You have all the mechanical components. So you have the wheels, the fasteners like the rivets, and you have a chain and everything. So this is a very good example of a complete design. All right, we're gonna go into the applications for CAD and mechanical design in general.
So what is CAD used for, and what does it become? So CAD designs are used a lot in industry and hobbyist applications. So professional industries always use CAD, and if you watch some YouTube videos and such, there are hobbyists that use Fusion 360 and similar applications to make hobbyist, toys and such. CAD will produce parts and assembly drawings, as discussed before, and they are also used for CNC manufacturing, which is computer numerical control, and that means that you tell a machine to make the part, and the machine automatically makes the part without too much human input. There's two types, subtractive manufacturing and additive manufacturing. So subtractive manufacturing are usually mills, routers, lathes, laser cutters, and water jet cutters. So you will be provided with some stock, so a sheet of aluminum, a chunk of wood, etc., and the machine will cut away at the material to produce what you want. And there's also additive manufacturing, which is usually 3D printing or casting. 3D printing can be plastic or metal. And when doing these things, when the designer and the engineering, when the engineer is making the CAD, they must keep in mind what tools they are going to use and make their tolerances and other parts to be manufacturable. So, for example, parts with overhangs cannot be manufactured with certain CNCs, and other more advanced CNCs can machine some overhangs. CADs are also used for presentation. So, for example, when your boss wants to see what you've done, you could present your CAD. Or when you are presenting your CAD to whoever is manufacturing it, you can show your CAD and present and tell them that this is what you will be manufacturing. And CADs are an easy way to provide a future part or system that will be made. All right, next.
I'm just gonna play this video. This is a CNC router. I don't know if it's gonna have any sound. Basically, you can see how a CNC router works. Sort of short, but you can sort of see that it's cutting away at this 0.25 inch stock of aluminum, right? And one thing I just wanted to add on, so a CNC mill and a lathe, there are versions of mills and lathes that are just CNC. So there are mills and lathes that you operate by hand, but these are, a computer is more accurate. And this machine, it looks very expensive. It is very expensive. It looks very advanced. It is very advanced. But even this machine, it has tolerances up to 3 thou, so 0.003 of an inch. And you're going to have to design your parts according to that.
All right, so CAM, the workflow. So CAM is computer-aided manufacturing opposed to computer-aided design. So this is the actual process where one will machine the part. So first, the designers use CAD software such as Autodesk Inventor to create part designs and generate step files. So step files is a type of CAD file, how a text file can be .txt or .doc. So .stp is a type of CAD file. And they will send these step files to the G-code programmers. And the G-code programmers can just be the CADers, and they will create a .tap or a G-code. And these G-code programmers create a G-code which tells the machine how to move their motors and such so that they can machine the part. And for example, this can be telling the CNC to move the X and Y motors a certain amount so that the mill can reach a certain place. And a lot of programs can mostly automatically do this, and the G-code programmers will run simulations to make sure that they are okay. You can also splice 3D printing G-code, and a lot of 3D printing G-code generators are super simple and easy to work with.
Yeah, so oh, I thought I was muted, sorry. This particular process that you see here is particular and specific to our robotics team. In the process could vary across different organizations. Maybe, if you're doing it by yourself, obviously you're not going to have all this, but the process is generally the same. um, Fusion 360 that you see here, it's also developed by the same company that makes Inventor, which is the CAD software that we use. And you the next slide has a good picture, but it can show you how to, or how it writes the G code. So you're not actually writing the G code. That would be a pain. And you can see here that's a CNC mill and that's a CNC router. And they serve different functions. They can serve the same function, but yeah, those are parts of CNC machining.
And the machine operator will set up the material and set up the machine to operate it, and then they can just start the machine, and they can be looking at the machine while it's printing or cutting, but most of the time you can have your eyes off of it. So the machining, you can machine the parts that you designed exactly the way you intended, and it's very important to see how your designs turn out in the real world. So to the right, the picture is Fusion 360 camming, and you can see thin lines that show where the tool will go, and that is the tool path. And whoever cams the part has to know the tolerances and the machine's capabilities to do it. It's the feeds and speeds, they're called, and it will tell the machine how fast to make it and how accurately to make it. It's important to see the designs, how they turn out in the real world. So on the, Kwan, you want to explain it?
Oh yeah. So I think it's really important, even as like engineers, and you might be making the CAD, but I think it's very important to see how your designs turn out in the real world. So in that picture, that's me and Kai, your presenters. That's when we were freshmen, and that's one of our robotics mentors and a former NASA engineer. We saw how our designs turned out, and you can see we're very happy. I think that's probably one of the most satisfying things of being doing mechanical design, is seeing what you made in a 3D CAD software, while you were sitting at home, in front of a screen, turn out in the real world. And it's also just a very important learning experience because you can see, what went wrong and you can improve on your designs later on. So that's sort of the reason why we were talking about this part, is because it doesn't really matter if you can do CAD design, if you can't make it in the real world, because you could have a CAD design, you could have a theoretical design, and you can present that and all, but if you don't have the data and the results to back it up, or you can't prove that as a good concept, then it's kind of useless. So that's why I think it's really important to learn and know the process and be able to go through it. Okay, so the next application, or I guess it's the first application, is robotics. So robotics is obviously building robots, but it combines many different engineering fields to create robots designed to do specific tasks. So it has mechanical engineering, obviously, but it has manufacturing engineering, electrical engineering, software and computer science is also a big part. Robots are hardware based in that what your robot can do is limited by the hardware that you make. So this is a presentation on CAD and mechanical design, and so it's going to focus on the hardware. And if your design is bad or it doesn't work, it doesn't matter if you have the best code in the world or the best wiring in the world or the most precise manufacturing in the world, because if the design is flawed, then your whole project is flawed. And so that's a way of saying that the software is limited by the hardware. Now, it's also true vice versa, where the hardware can be limited by the software, in that you could have a fancy piece of steel and aluminum, and it looks really nice and well pocketed, and it's very light and it doesn't cost a lot of money. But if you have bad code, or the software team can't support it well, then it's not going to be able to work, right? But in the flow and the process, the hardware comes first, and so it's very, very crucial that you get the design right. And it's also a lot harder to fix hardware. If your code isn't working, then obviously you can debug it, you can see what's wrong, and it's just lines of text. As long as you don't like smash the intake on the ground, you're fine. But hardware based, if it's flawed, it's gonna take more time to redesign, remanufacture, refabricate everything. So your job, when doing mechanical design, it's very important. So here's some examples of robots from different levels, right? So on the very left, that's a CAD render of the Mars 2020 rover, that's launching on July 30th, I think, and it's gonna take about 79 months, I think, to go to Mars. That's probably one of the highest level CADs that like you'll ever see, right? It has all the electronics, it has all the pneumatics necessary, it has all the motors. The drivetrain, incidentally, this design is called the rocker bogie design, and we actually used it in 2016. But anyways, this is a really good example of how CAD is used in very professional, high level applications, right? And on the middle and right, you can see CAD renders of our robotics team 2637's 2020 and 2019 robots. Again, this also has all the pneumatics and all the electronics in it, but you can see it's a lot simpler than the Mars robot. But either way, they're both using CAD and they're both following the same process. The scale is different, but the process is the same. And I think it's really cool to see how you could be chugging away at a CAD for your own application, or maybe for a team, and then also see something similar happen in somewhere like NASA. So those are just examples of how robots interact or are in the world. And also, the next application, probably more relevant to you guys, is research, right? So this is the design of a mechanical ventilator. Of the main, quote unquote main, I'll say IgniteMinds projects, I think mechanical ventilators are the most alike to what we're presenting now. And this one was a designer pulled off a patent. So it's by Douglas F. DeVries and Todd Allam, and that's the US patent if you want to look it up later. But anyways, this patent was granted in 2012 for a mechanical ventilation system utilizing a bias valve. And so you might be like, what's a bias valve? So a bias valve, it's also called a proportioning valve. It's a type of valve that supplies a reduced or tapered pressure. So if you graph the pressure that a certain output is experiencing, the graph will eventually taper out, and that tapering is due to a bias valve. And these are used, for example, in the car, on the brakes, so that when you slam on the brakes don't lock up, and instead, and they're designed to at least not lock up, and to reduce the pressure that's on the brakes. This particular design also includes a flow meter operative to measure the gas flow. So if you're designing a ventilator, you'll know that you need to be able to control the flow, the gas flow, and the pressure or the volume or both, to make sure that the patient, is gonna survive basically. And this particular design also has an ECM, an exhalation control module, that operates an exhalation valve. But this figure is the proportioning valve, and you can see how mechanical design engineers and CAD is used for research projects. So what we talked about, a lot of it might seem like, oh, it's about robotics teams. That's not exactly true. There's a big application of it in research. Research isn't always just a biomedical lab. Um, this is also a large part of it. And so finally, next steps. I broke it up into two categories, so ventilator design and other robotics/mechanical engineering related things. So first, for ventilators, there's engineers around the world. I think it started in Ireland, but they're collaborating on an open source ventilator design that's low cost. It's lower functioning, which is sort of our research project to modify that. But it's collaborating on open source ventilator design, and the link is there. You can see it when you get the presentation yourselves. To increase accessibility and lower the cost of ventilators, due to the ventilator shortage, due to the pandemic. I saw on the news today that America was running out of personal protective equipment, and there's still a ventilator shortage, so there's definitely still a need for this. And it would also just be a very good project to try to pursue for future, or to prepare against future epidemics and pandemics, because a ventilator costs tens of thousands of dollars. If you have a low cost, high performance alternative, it'll be really great. To get started, you can download CADs online for inspiration, and you can look at patents from higher end ventilators. I'm not sure about that exact link because that's an article, but there was also another link. I'll pop it in chat if I find it, where you can download even more resources besides just the CAD. You can get bill of materials, which is all the materials used in the assembly and the cost associated with it. You can look at the PCB drawings. So PCB is a printed circuit board, and that's going to control a lot of the functions of the ventilator, and manufacturing fixtures. So that would be like guides on how to fabricate it, right? And these are all open source, free for everybody, and that could help you get started very quickly. In terms of other robotics and mechanical engineering related stuff, you first really have to look at two things: what you have access to and what your goal is. If you're looking to build a functional prototype, and I use functional prototype in the sense that it's an idea. You're gonna be able to build something that isn't polished aluminum, but it's gonna work. It's gonna move, and you're gonna be able to control it somehow. How far do you want to go with this, right? Do you want 3D print pieces? If so, do you have access to a 3D printer? Do you know someone that has access to a 3D printer? PCB design, do you want to design a printed circuit board and buy a buy the design, basically etched design of it, or do you want to go with an Arduino? And depending on the scope and goals of your project and the resources that you have, feel free to contact us and we'll try to make something work. So that transitions into the resources that you have currently to get started.
So for learning CAD, you have to first choose a CAD package. So which CAD software do you want to use? There are plenty of student licenses available, especially for like Artist Inventor. There are lots of popular CAD packages such as SolidWorks, Creo, Artist Fusion 360. There are others that are not so much professional CAD, but more like hobbyist CAD, and you can use uh, very low level CAD software such as Tinkercad um, and such. There are plenty of tutorials online, but hands-on experience is the best. So I would recommend downloading a CAD software and trying to stick to it and trying out all the different features. Um, you don't need to use all the cool features, and some things can be done in more ways than one. So trying to make your own system, own CAD yourself is the best way in my opinion to learn. So if you can design a small system and hold design reviews. So design reviews are uh, reviews that you hold as the designer and invite others to criticize your design and provide feedback. And this is one of the best ways to learn and you can see what mistakes you've made and try not to make those mistakes in the future. Uh, you can join a team to further your skills, such as the IgniteMinds project, and as mentors, we can we can conduct design reviews to provide you with feedback and contact other people to also join in on your design review. You can join a robotics team, and there are plenty of people there, other students and mentors from the industry to uh, conduct design reviews for you.
Yeah. So, most of what we talked about, we learned or was started from uh, learning within the robotics team, um, Team 2637. And, as you can see, it's been pretty helpful. One thing I wanted to add on, Autodesk Inventor and SolidWorks are very similar. Um, in most colleges, SolidWorks is taught if you're going for an engineering degree. Um, Creo is mostly for architectural, but I know teams that use it to CAD the robot. There's also a cloud-based system. So Fusion 360 is cloud-based, but it's like a baby version of Inventor. Um,
There's Onshape.
yeah, Onshape is another bigger cloud-based one. All these are free, by the way, for student licenses. And if you go into the higher professional or higher graduate and college, possibly levels, there's other softwares like NX, but I think you'd mostly want to stick with the ones we discussed before.
There's some game developers that use Blender to make their characters or environment, for
Mhm.
example.
Oh, and that's me making the drawing that we showed you before. That was
No, you didn't
horribly
make the drawing
complex.
though.
Well,
I made the drawing.
yeah, I printed it.
That's you
Um,
printing it.
and applying your research, right? So you can spend lots of hours reading through research papers and patents, like how we did. But what do you do next? First, you should find CAD models of your project and look at it in your CAD program. Being able to orbit around and look at the exact facets of design is very helpful. And once you look at those designs, um, brainstorm any improvements that you could make, right? Um, it doesn't have to be solely about performance. Maybe you can lower the cost of the material. Maybe you can lower the uh, barrier to entry. Um, there's a lot of things that you can improve on design. No design is perfect, and everything has trade offs. And then maybe you want to develop prototypes as a proof of concept. This is sort of what we talked about before. You could 3D print and you can use an Arduino to control, but maybe you just want to CAD it and show that it's possible. Again, it depends on the resources you have and the scope of your project, but throughout all of this, if you're gonna pursue it within IgniteMinds, we'll be to help you. We'll be happy to help you. If you have any questions, you can contact us here. or you can DM us through Discord. I think you can do it through the IgniteMinds server. And here are just some of the acknowledgements for some of the inspirations that we had, and where we owe a lot of it to. Does anyone have any questions, comments, concerns? Anything you want to give us feedback on or anything?
I have a quick question.
Mm-hmm.
So you mentioned that you could download CADs for inspirations. Where could you download them from?
Okay, so usually, if it's like a ventilator, for example, and it's an open source ventilator, then you just type in mechanical ventilator design, or low cost or something like that. You just type in CAD after it, or SDP file, and they usually show up. If not, or you're looking at a different specific part, so if you wanted to add like a certain valve to your design, then you can search up, like, for example, bias valve, and then CAD or step file. And GrabCAD is a great resource. If you don't know what GrabCAD is, it's a place where engineers share their designs to the world for free. And I think if you make an account, you can just download them for free. You have to make sure that the files are compatible with your CAD package, but usually they are. Would it be okay to incorporate open source CAD designs into your final CAD model? So it depends on like what you're gonna do with it. If you're gonna like apply for a patent, which is something that like we've discussed before, I think you'd have to look at it more. But I think in general, if you are improving upon a design and it's open source, then I think it should be fine. Oh, Aksha's here. Does anyone else have any questions? All right. I guess not then. Again, if you have anything that comes up later, feel free to contact us. Our info's there, and we'll also send out the presentation so that you can access it later. Cool. Thank you guys all for coming then. Kyle, you have any last words?
Nope.